Hello. Today we're going to get started with our mathematical material in this class. We're going to start out in Unit 1 by reviewing some operations that we need to know for the rest of the class. And a big one is exponents. So exponents are just a shorthand for repeated multiplication. Just like multiplication is shorthand for repeated addition. So instead of writing 2 plus 2 plus 2 plus 2 plus 2, I can just write 5 times 2. So multiplication is shorthand for repeated addition. Instead of writing 2 times 2 times 2 times 2 times 2, I can write 2 to the 5th power. So exponents are just a shortcut for repeated multiplication, or x times x times x times x. Instead, I could write that as x to the 4th. So this is my definition of exponents, is we're going to just use it to make our lives easier. We'll have to write expressions like this one a whole lot, and so it's easier if we can write it this way. I just want to mention right now that definitions are human inventions. All of the definitions in this class were invented at some point in the past because they made our lives easier, just like this one. They were invented to solve some problem or to meet some need. And every definition is like that, not just in mathematics. So be careful, beware of people who start an argument by saying you have to use their definitions. A definition isn't more correct because it's in the dictionary. Definitions are, they're tools, and you should be aware that you can make your own tools if you want. If you're thinking hard about a subject and you can't find a word that does what you want, make up your own word. It can be really helpful in clarifying your thought. So what I want to do now is take this tool and look at some of the consequences of inventing it. We started with a simple definition, but we're going to end up with some rich behavior. Let's see. So the parts of this expression, if I write something like 2 to the 5th, I'm going to call the number 2 the base. And this little 5 here, we could call it the power or the exponent. I have some terminology like this throughout the course just to make sure we're all talking the same language. So I could read this expression as 2 to the 5th power, or 2 raised to the 5th power. If I raise a number to the 2nd power, it's like saying that it's squared. So I say 4 squared is 16. There's a reason for that. If I draw a square and the side lengths are 4, then the area is 16 square units. So that's where that term comes from. That's why we call this squared. And you might have seen something like this. If I write 5 cubed is 125. Well, the reason I call that cubed, you guessed it, if I draw a cube where all of the sides are length 5, so this is 5 and this is 5 and this is 5, then the area inside is 125 cubic units. So those are a couple of special names, but that's enough terminology for now. Let's look at what we can do with these things. So we're going to come up with shortcuts for simplifying expressions in the future. For example, if I write something like 2 to the 5th times 2 to the 6th, what would that be equal to? Well, long way to go about doing this is to say 2 to the 5th, 2 times 2 times 2 times 2 times 2. That's 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. And in the same way, 2 to the 6th is 64. We're going to have to do some long multiplication here, but this turns out to be 2048. But there's a better way. See, when I write 2 to the 5th, what I mean is, so let's use this as a consequence of the definition. What I mean is 2 times 2 times 2 times 2 times 2. There are 5 2's. And when I write 2 to the 6th, I mean 2 times 2 times 2 times 2 times 2 times 2. That's 6 2's. So altogether, there are 11 2's here. There's 5 2's on the left plus 6 2's on the right. So altogether, there's 11 2's, and I could write my answer as 2 to the 11th power, which happens to be 2048. See, math is consistent. As long as you're doing math correctly, No matter which way you choose to solve a problem, you'll get the same answer. We'll see a lot of problems this semester where there are two completely different ways to solve it, maybe 3 or 4 completely different ways, but they always get the same answer. That's something that's special about math. That's one of the things I really like about it. But what we're seeing here is we started with this simple definition. Exponents were just going to be a way to write repeated multiplication faster. But what we got is if I multiply 2 expressions with the same base, since this is 5 2's and this is 6 2's, it's like I can add their exponent. So we can write this down as a rule. As long as you have the same base, let's call that base b. This works for any number, not just 2. If I have m copies of b, and I multiply that by n copies of b, I'm always going to have m plus n copies of b. So multiplication outside of the exponent is the same as addition inside of the exponent. This is a property of exponents. It doesn't just work for 2, 5, and 6. It works for any 3 numbers. This is that abstraction I was telling you about in the introduction video. Mathematicians don't just want to say, what's 2 to the 5th times 2 to the 6th, and then start all over from scratch if you ask, what's 3 to the 8th times 3 to the 9th. We want to, once and for all, solve every problem of that type. We do that with variables. A variable is a way to talk about a number without saying what number it is. So variables follow all the same rules as numbers, except that we don't know what number they are. So here I'm saying no matter what 3 numbers I pick, b, m, and n, I have m copies of b here and n copies of b here. So together I must have m plus n copies of b. So this is the first of our exponent properties. I'll put a table at the bottom of the notes, but we're about to make 5 or 6 of these, I think, different exponent properties. For example, what would I get if I asked for 3 to the 7th divided by 3 to the 4th? Well, up top, I have 7 copies of 3. And down below, I have 4 copies of 3. So I'm using a specific example just because it's easier to work with numbers than with variables. But in the end, there's nothing special about 3, 4, and 7 that makes this next bit work. I can cancel out all of these 3's down here with these 3's up here. Anytime something is multiplied by both the numerator and denominator, you can cancel it right out. So the numerator was multiplied by 4 3's and the denominator was 4 3's. We can cancel out those 4 3's. And what we're left with is 3 3's. And the reason we have 3 3's left is that there were 7 on the top and 4 on the bottom. When we canceled out, we took 4 away from the 7. So this 3 is here because 3 is 7 minus 4. Now, like I said a moment ago, there's nothing special about 7, 4, and 3 that made this work. This would work with any 3 numbers. If I have b to the power of m divided by b to the power of n, I'm using b for the base, m and n for my powers or exponents. I'm taking n copies of b away from the m copies of b, canceling them, and I should have m minus n copies of b left. You could call this the quotient property of exponents if you wanted. This top one you might want to call the product property of exponents. The names of these things are not so important. In English, I like to think of math as its own language, and the equation is its own name in the language of mathematics if you think about it that way. So these are useful properties to keep in mind. Multiplication outside is addition inside, and division outside is subtraction inside. That's because we had m copies of b, and we took away n copies. I like this method a lot better than saying, oh, 3 to the 7th power, that's, let's see, 3 to the 4th power is 81, 5th power is 243, 6th power would be 729, and 7th power would be 2,187, 3 to the 4th power would be 81, and then we'll be stuck doing long division all day to get what we already know, that the answer is 27. So, knowing these shortcuts gives you a much faster way to work with things. So we've got an immediate application that we want to be able to work with exponents a lot faster than we would if we were turning everything back into numbers. we've got the more distant application, or the more big picture thing, that I just think it's really neat, the emergent complexity. We started with such a simple definition, and we've already got these interesting rules. Now let's develop some more of them then. If at any point during this lecture, since this is pre-recorded, if you get confused, you can try rewatching. If that doesn't help, maybe pause and try to work something out yourself that looks like what I've just done. And if none of that is working, write down your question and bring it to the next office hours, and I'll be happy to help you there. You could also email me the question, but I prefer office hours because that way if anyone else has the same question, they can see the answer as well. Okay. Now, here's something funny. What about, say, 3 to the 6th divided by 3 to the 8th? Well, according to the rule we just saw, that should be 3 to the power of 6 minus 8, which is 3 to the negative 2. This is a kind of expression that we haven't seen yet, a negative exponent. What's that going to do? Well, there were 6 3's on top and 8 3's down below, and the 6 canceled with the 8, and that left 2 3's down below. Once everything canceled, you see? Just like this, except there were 2 3's left on the bottom instead of 3 3's left on the top, because there were 2 more down here than up here. So what I'm seeing is that 3 to the negative 2 has to be the same as 3 squared. This is called a transitive situation. This is the transitive property of inequality. If the first thing is equal to the second thing, and the second thing is equal to the third thing, and the third thing is equal to the fourth thing, and so on, then the first thing has to be equal to the fourth thing. We can transition from this equal sign to this equal sign to this equal sign. So that's called the transitive property of equality. And it's pretty helpful. What it means is I can just cut out the middleman and say 1 over 3 squared is the same as 3 to the negative 2. So when I write 3 to the negative 2, what I really mean is 2 copies of 3, but in the denominator instead of the numerator. So a negative exponent is going to put the expression in a denominator. Like if I wrote, if I wrote 4 to the negative 1, that's the same as 1/4. Or if I wrote 2 to the negative 4th, that'll be 1 over 2 to the 4th, so it's 1 over 16. Make sense? Oh, why did I ask? No one's here to answer. Hopefully that makes sense. If it doesn't, please do ask me during office hours. Now, this is cool. We can treat negative exponents, now that we know how to work with them. We can use either of these rules with negative exponents. So if I wrote x cubed times x to the negative 2, I can treat this with our first product property and say that's the same as x to the, whoops, that's not an x to the 3 plus negative 2, so that's x to the 1. Haven't seen this expression yet. X to the first power, what could that be? Yep, that's right. There's 1 copy of x, so 1 copy of x is just x. Now, x could have been any number here. Any number to the first power is that same number. So 5 to the first power is 5, 11 to the first power is 11. All right. So that's our product property. Anything else I want to say here? Nope. All right. A little bit of language I want to come up with here. What's the difference between 5 to the 5th plus 5 squared over 5 and 5 to the 5th times 5 squared over 5? Two different expressions. The answers are going to be 2 different numbers. See, the first one, oh geez, 5 to the 5th, that's a big number. It's 3125, it turns out. So if I want to just solve these numerically, I could write that this one is 3125, 5 squared is 25, all divided by 5. So that's 3150 over 5, which is 630. And this second one here, 5 to the 5th times 5 squared, oh, that's an even bigger number. 5 to the 5th times 5 squared. Oh, snap. I made a mistake in the first part. 3125 is 5 to the 6th, not 5 to the 5th. That's why I was confused. So this should be 625. No, I was right the first time. Oh my goodness. No, this is 3150 over 5 is 630. Let's see, 3125 times 5 is 15,625. Times 5 is, let's see, this one will be 78,125. Okay. So this one right here is 78,125 over 5, which is 15,625. So these have different values. I mean, of course they do. There's an addition here and there's a multiplication here. If I want to work on these with shortcuts, though, this one on the right here, I can write 5 to the 5th times 5 squared over 5. Well, 5 is 5 to the 1st, so I'm going to put a little 1 right there. This is 5 to the power of 5 minus 2 divided by 5 to the, or 5 plus 2 divided by 5 to the 1. I use the exponent, or the product property up here, multiply these two things with the same base, and we can add the exponents. If we're dividing, we can subtract the exponents, so this is 5 to the power of 5 plus 2 minus 1, which is 5 to the 6th, which is 15625. Over on the left, this is not the same as 5 to the 4th plus 5 to the 1st. 5 to the 4th plus 5 to the 1st. Oh, sorry. What am I saying? It's exactly the same as 5 to the 4th plus 5 to the 1st. My goodness. This one's not the same as 5 to the 4th times 5 to the 1st. This one, 5 to the 5th plus 5 squared over 5. Let me make an argument from analogy real quick. If I had a pizza cut into 8 slices and I had 2 of the eighths and then you had 3 of the eighths, together we have 5 slices of pizza. This is 2 plus 3 over 8. In the same way, if you have 5 to the 5th fifths and I have 5 squared fifths, together we have 5 to the 5th fifths and 5 squared fifths. What I'm trying to say is that you can always break up a fraction over addition. And here's where I want to introduce some terminology. When I have two things added together, I'll call those terms. So I have a 5 to the 5th term and a 5 squared term, and they make a sum. When I have two things multiplied to make a product, I'll call them each factors in this class. So I have a factor of 5 to the 5th multiplied by a factor of 5 squared, and then we divided that by a factor of 5. When I have terms, though, I need to divide both of these terms by 5. So the 5 comes out of every term. Just be careful when you're simplifying this. If you just cross out this 5 and one of these 5s, that'll not be correct. So it's not the same as 5 to the 4th plus 5 squared. 5 has to come out of both terms. So the distributive property, if you've seen that. If you haven't, we'll talk about it very soon. So our final answer is 5 to the 4th plus 5 to the 1st, which is 630. Same answer as we got up above here. One other thing we can do, there's a very careful way to cancel these things. See, if I have, let's say, x cubed times y to the 4th divided by x squared, I can just say 2 copies of x came out of the denominator and 2 copies of x came out of the numerator. So I have x times y to the 4th. If the entire numerator is one term, like it is here, it's not added to anything else, there's only one term in the numerator, then you can just pull the denominator out of the whole thing. But if there's multiple terms, like when I had 5 to the 5th plus 5 squared over 5, you have to pull this denominator out of every term. Here's a long run around that to help it make more sense. Instead, I'm going to factor this 5 out of the numerator. So I'm going to say the numerator is equal to 5 times what? 5 to the 5th becomes a 5 to the 4th, and 5 squared becomes a 5 to the 1st. So that way, 5 times 5 to the 4th, if we distribute, that's 5 to the 5th. 5 times 5 to the 1st is 5 squared. It should be a plus, of course. So 5 times 5 to the 4th plus 5 times 5 to the 1st is 5 to the 5th plus 5 squared, all divided by 5. And now I can cancel factors. You can cancel out a factor from the numerator and denominator, no problem. Can't cancel out a term, but we can cancel out a factor. So if you factor the thing you want to cancel out of the entire numerator, that's a very safe way of factoring. And look, we get the same answer, 630. A third way to get that. We'll talk more about careful canceling in a bit, but before we do, I have some other things I'd like to show you. Let's take a look at, where to next? Well, what do I do if if an exponent is 0? That'll be the next rule we examine. If I write 3 to the power of 0, you might remember that this is 1. Where could a 0 come from, though? Well, this is the same as 3 to the power of 4 minus 4, which is 3 to the 4th in the numerator and 3 to the 4th in the denominator, right? So I'm using my quotient property, but in the other direction. Since I subtracted them inside the exponent, that's the same as dividing them outside. With either of these properties, to use one of these properties, what you do is you say, I found this in my work, I can replace it with this, or if I found this in my work, I can replace it with this. You can go either way with any equation in mathematics. Very handy. So here, I've replaced subtraction inside the exponent with a quotient outside. And of course, since the numerator and denominator are the same, we can cancel them out and get an answer of 1. So anything to the 0 power is 1. But I have to be careful. This argument, unlike the others, it does depend on something special about 3. Not very special. It would work with 2. 2 to the 4th over 2 to the 4th is 1. 5 to the 4th over 5 to the 4th is 1. But where it doesn't work is 0. If I try to write 0 to the 0 is 0 to the 4 minus 4. That's 0 to the 4th over 0 to the 4th. I'm in trouble because we can't divide by 0. So any other number to the 0 power is 1. This argument works for any number 3, 2, 5, negative 10, except for 0. So 0 to the 0, we're going to write does not exist. It's undefined. There is no way to work with that expression. It's not a number. Excuse me. Let's see. Here's another handy exponent rule. I call this next one nested exponents. And what I mean is you have one exponent inside of another one. For example, if I wrote 2 cubed to the 4th power, well, what I'm saying is I have 4 copies of 2 cubed. So I have a 2 cubed, another 2 cubed, a third 2 cubed, and a fourth, whoops, not a 4, a fourth 2 cubed. Well, but each 2 cubed is 3 copies of 2. We have 3 copies of 2, and then another 3 copies of 2, and then another 3 copies of 2, and then a fourth 3 copies of 2. How many 2s are there altogether? 12, of course. Like we saw a minute ago, our final answer is going to be 2048. So I got 12 copies of 2 because there were 4 groups of 3. When I say 4 groups of 3, what I mean is 4 times 3. So this 12 is here because 12 is equal to 4 times 3. And this argument didn't depend on anything special about 2, 3, and 4. If I say I have b to the power of m, and I take that to the power of n, well, I have m copies of b written out n times. So altogether, I should have m times n copies of b. So I call this the nested exponents rule. Here's a fun little extra bit to the nested exponents rule. B to the m times n, multiplication is commutative, which means I can multiply in either order and still have the same answer. So for example, 3 times 4 is the same as 4 times 3, of course. But I can write this as b to the n to the power of m. So whenever you have nested exponents, you can change their order if it's convenient. So instead of writing 2 to the 3 to the 4 here, this is going to be the same as 2 to the 4 to the 3. We'll see a couple of examples later this semester where this property is incredibly convenient. So that's called the nested exponents property. Let's see. I believe I have... Aha! I do. I do want to talk a little bit about the distributive property, but before I do, just want to point out, now we've got 5 different properties. We know that if I add inside the exponent, that's the same as multiplying outside. We know that if I subtract inside the exponent, that's the same as dividing on the outside. We know that anything to the power of 1 is that same number. We know that anything to the power of 0, well, except for 0 itself, is 1. And we just found out that b to the m to the n nested exponents are the same as multiplying those exponents. So from a simple definition, we've got these 5 different cool properties, and we'll come up with a couple more in the next lesson. But I'm going to take a slight break now, and we'll be right back with the next part of section 1.2. I'll see you in a moment.